Tomorrow we have a mechanics exam, so I'd like to go over the topics for the entire course, which is quite a bit. In the first quadrant over here, we see that we're dealing with actions and Lagrangians. So, Lagrangian is just kinetic minus potential. And Hamilton's principle allows us to take the stationary action. So we're taking a variation in the action, setting it equal to zero. And that's kind of what that looks like over here, as you can see. It's like we're going from one point to another point, and we should have a straight line. So we're looking for a zero variation, meaning that this little squiggly line around it would essentially disappear. So from that, we can get the Euler-Lagrange equations by taking some derivatives in terms of velocity and in terms of the base, which in this case I put the base as x, although sometimes it's the base of t. And so from the Lagrangian, we can find some derivatives. As you can see here, if we take the derivative of Lagrangian with terms of velocity, then we get the momentum. Take the derivative in terms of position, then we get a force. The Euler-Lagrange equation does solve weird integrals, so as you can see, if we get some kind of weird integral like this, maybe the Euler-Lagrange equation uh, can essentially solve this. I mean, the variation can solve this. Taking the variation allows you to solve weird integrals. Um, so here's the Beltrami identity. So if there's no explicit t, or in some cases x, in the base, as you can see, we have sort of the Lagrangian in terms of q and q prime, although we're taking an integral for the time, and time isn't even in here, then we're able to say that, okay, if there's no time dependence, then Hamiltonian, which is equal to the sum of the energy, is equal to a constant. Oops. And since it's constant, we have this situation we can do. We can do q prime times the momentum minus Lagrangian is equal to the constant. So this is just kind of a shortcut, just in case there's no explicit t in the Lagrangian. Um, let's do a quick review of the Brachistochrome cycloid because we start maybe here at some potential. We get to this kinetic energy over here, so we can minimize this action in terms of time, minimum time. And when we do that, we have to use the Beltrami at some point, because notice how this Lagrangian, you're integrating over x, but there's no x in it. So we're using this type of Beltrami identity like we just talked about. And when we solve this, I mean, that's the hard step. Putting it, then we have to do a little integral and find the equations of motion. So the equations of motions are called extremals because, well, I guess it's probably because we're setting the action equal to zero or the variation equal to zero. Okay, so we have this kind of motion and we do the cycloid, which is cool. That's essentially, this little setup here, along with the Lagrangian and the Euler-Lagrange equations and Beltrami identity, allows us to pull out these equations of motion from this setup, which is crazy. Here's how we can do a simple replacement. This isn't all that important. But what's really important is the idea of constraints and applied forces. So clearly, the total force is the sum of the applied plus the constraint. And the idea is that these constraint forces do no work because they're perpendicular. So you can do this F dot dr equals 0 thing. And when you try to put the total force all in there, what happens is the only thing that remains is the applied force because the constraint force does no work. So and then you have this equation, which leads us to the Euler-Lagrange equations. Cool. Holonomic means it's just coordinate based, and non-holonomic means you got velocities instead. Now, about these constraint forces, usually we have to set up a slightly different modification of the equation. You can either modify the Lagrangian and then just use the regular equations right here. So you can see we added a Lagrange multiplier times the constraint, which is this. And of course, it's important to find the derivative of the constraints. So then we have but I prefer this version here where you sort of use the original Lagrangian and then you just modify the equation by doing this little thing here. And then you get the constraint, which is the Lagrange multiplier times this partial derivative here. And as you can see, if we analyze these, the idea is that the Euler-Lagrange equations is equal to the applied force, which is interesting because these are slightly controversial. It's either equal to the constraint or it's equal to the applied. I guess I'm a little confused about that. But anyway, so if we look at this F in terms of X here, like that's a tension. That's a tension force, which is the constraint force here. And then if you think about it in terms of the angular derivative, then we would get a torque because it would be sort of like sideways. In any case, as you can see, this is how we can interpret these equations. I'm still a little confused about whether this is applied or constraint. So I don't know about all that. But I guess they each have, okay, the constraint forces each have their own Lagrange multiplier. And the applied forces are F dotted with dr over dqi. I don't know, we didn't really work too much with applied forces, so I don't have a lot of information about that, but I do have the constraint idea here. Alrighty then, so so that's kind of the Lagrangian situation. Now, the cool thing about Lagrangians is that you're able to solve really complex systems, but so it's important to choose good coordinate systems. Like r hat equals cosine plus sine, theta hat equals this, and then you want to take some derivatives out of that. You can do all these cool little transformations, which is fine. But the point of the Lagrangian is that first you have to find, I think it's more down here that we have to look at. First you have to find velocities. And the velocities require squaring the positions, or squaring the derivative of the positions. So like setting up a good Lagrangian requires knowing how, first of all, how to set up the good positions for these coordinate systems, which is why I have a couple different coordinate systems set up all over the place. Because each one just has such a unique way to set up these systems. But we'll talk about the velocity here. In Cartesian, cylindrical, spherical, once you have the positions, then the velocities are relatively simple because you just square them. And if you're in Cartesian course, it's pretty easy. You do x prime squared, y prime squared, and z prime squared. Cylindrical is a little bit harder because you have to put like uh, r prime here, and then r times this theta prime, and then plus the z prime, and this term is squared. And then we have the spherical, which is just r prime squared plus r theta squared, and and then you have this r sine theta phi prime squared. So this is whatever. But let's think about the coordinates now, because coordinates are a little bit harder to determine. So we have all these different examples for coordinate systems. So we'll start with this Atwood machine, for example. So the Atwood machine usually has one going down in x, the heavier one, and then one going up, and we would think of it as L minus x, the length of the string minus this distance, gives you the other side. So we kind of set that up. Pretty simple coordinate system. This coordinate right here, it's rotating in a way where equilibrium means that there's no change of the radius, and the radius is the distance across here. W is going to be equal to phi prime, and over here for, not sure if we could see this quite easily because I got like my picture in the way as well. This particular one here, in the chat window, as you can see, we have like this z-axis pole, and then we have a hoop that's like spinning around from this point, and that's quite complicated. All right on. Hey, how's it going, Griffin? Uh, thanks for showing up for the review video. And it's cool that you're using the VM sheets. Right on, dude. Yeah, I got my chat window set up. Awesome. Let's keep going here. So this thing is spinning around this z-axis, and it's a little hard to set this up for this bead because we got this hoop over here and this theta from the hoop. So hopefully this is correct. That x, y, and z can be set up like a coordinate system here. R sine theta cosine of this, and then r sine theta sine of this, and then r cosine of theta. Hopefully this is correct, although it's a little difficult to even verify. So, so yeah, I guess this is in like spherical coordinates in some way. Yeah, it's a little difficult. So that's that system. And as you can see, it's not always so easy to figure out what the coordinates are. Let's try another one. So this one is basically, I think it's the same picture written in a different way. So here we have a point where this, it's kind of like the z-axis, where this hoop is rotating around it, and we can draw a line here to there, calling it R. I'm pretty sure this is the same exact setup as the one we just looked at, maybe in a different context, different coordinate system. R is going to be equal to the vector from P to the origin and then origin to B. And if you want to add up those vectors, well, this is R. Uh, the first one is PO from here to there. You see we have an x coordinate, which is R cosine WT. And then the y is R sine WT. And then we have to add the next vector, which goes from here to there. But notice how we have two angles here? Because we have the original WT angle, and then we have this phi angle. So we have to add both the angles when we set up the R cosine and R sine. Now this makes a really complicated coordinate system, but hey, at least we have our position. From there, we can take the derivative, and then we can square it, and we can get the Lagrangian. So Yeah, that's a little bit more intuitive than the previous setup. There's more. This has to do with orbiting, kind of has to do with a little bit later. Here's another one. And we've already sort of looked at this with the pendulum that is twisted to the side here. But the way we want to think about this is just 1/2 mv squared minus mgy. And of course, y is going to be like r minus r cosine theta, x is r sine theta, and the v squared. Remember, we kind of get the idea that we have to take um, um, this is x prime squared, and this is y prime squared. It's just that I forgot to put it here, because x prime is actually, um, there's small angle approximations going on here, I think. XW. Oops, these are difficult. Now, the idea is again that we're just supposed to take a v squared equals um, this is an arc length, arc theta, and you take the derivative squared. XW is the same thing in, in a different direction. So we have the same idea here, just going in two different directions. I guess that's how we have to think about this. It's really difficult to set up these coordinate systems. So this is for coupled oscillators, which we should get into later. But where are we at? I think at this point we might just need to go into take note of these path integrals here. If you're solving these variations, ds squared equals dx squared plus dy squared, the polar version, the cylindrical version, and the spherical version. And let's discuss this circular orbit. So with circular orbits, we have like the total energy of the system here, which is the sum of the center of mass velocity plus the relative velocity between them plus the potential energy also between them. Now, this usually has to do with some sort of central force that causes this uh, orbit. And the central force is always in the r direction. It's like the point. Actually, the definition of the central force is that it's in the r direction. It's also the negative derivative of potential, the effective potential. And how do we get this effective potential? Well, let's realize that if we wanted to, first of all, go into the center of mass frame, meaning in the center of mass frame, this r, capital R prime, is 0 because we've put ourselves in the position of the center of mass. So, like, our velocity relative to us is always 0. So if we put ourselves in the center of mass position, then the center of mass velocity is 0. Like, we can't measure our own velocity, only external things can measure that. So we go into the center of mass, meaning that we have to focus on the relative stuff. And notice how this is a small r vector, and these are not vectors. These are the r's. Now it's a little confusing, but when you go into polar coordinates, I think we discussed that over here. this particular equation here in cylindrical explains how we have to take our r vector squared, and it's actually equal to, I guess this makes a little more sense. It's equal to the r. The reason why I put a p here is because of this whole idea is that because it's r squared, r prime squared plus r times the, like, this is the magnitude, but not the vector. So when you put it into polar coordinates like this, then it breaks apart, and instead of a vector, it becomes r prime squared plus r squared theta prime squared. And this is the kinetic energy right here, right? But what we're going to do is we're going to remove the theta component from the kinetic energy, and we're actually going to replace it with the centrifugal barrier, the angular momentum. So you stick that in there instead of theta, and it becomes L squared over 2 mu r squared. And this has no theta in it. It's actually has no velocity either. It's dependent on r. Because it's dependent on r, we can sort of shove it together with the potential energy and we call it U effective. So then this is ultimately the energy after compactification here, where we sort of switched into the center of the relative velocity frame, not the frame, the relative velocity. We're like analyzing the relative velocity and we see the U effective, which is this. So that's cool. And anytime that we have a potential that's like circular, take the potential and add L squared over 2mr squared. You always have to add this anytime there's a central potential. Um, so that's cool. Now there's some more stuff here, like how we can figure out the W of oscillation. Notice that it's the U effective double primed over mu. Notice that we can find, like, the first derivative tells you that it's a circle. Oh my god. The first derivative tells you it's a circle. The second derivative, if it's positive, it tells you that it's stable. So here's some directions we're trying to solve this. First, add the centrifugal term and find turning points on the boundaries and like the potential levels. Then you can analyze stability after that. For the eccentricity stuff, here's the orbit equation. So this is like r theta, something's orbiting around. You can kind of see the orbit right here. It's not circular unless like unless epsilon equals 0. It's more elliptical if we have some sort of an epsilon, some sort of eccentricity. Also, the energy would be less than 0. It's parabolic if the energy equals 0 and the eccentricity equals 1. And it's hyperbolic if the eccentricity is greater than 1, meaning the energy is greater than 0. And this is exactly what we want to put here, which means either L squared over mu y. And what's y? Y is usually mg with some force constant. We have A, that's going to be the axial, major axial, or semi-major axial. And we can stick that all into this equation. It's getting a little bit complicated here. So Rmin and Rmax are going to be essentially Rmin, Rmax. There's some equations for that. Involving eccentricity. We have to consider the bound circle, the bounding ellipses. Unless they're equal to each other, sometimes define a point of the r velocity, r along its velocity at that point, set that equal to the bound equation, and there's some more equations over here, like the thrust factors, where we sort of have to move between one orbit to another orbit. And we want to use the vis viva equation for that, v squared equals gm 2 over r minus 1 over a. Okay. Maybe one more look here at the center of mass and the reduced mass. Notice how we have to take this r, which is the difference between these two vectors, and translate it from the kinetic energy in terms of R1 and R2. We want to translate that into the kinetic energy of the center of mass and the relative frame. Something like this. And here's R1 and R2, and here's what we want it to look like. So here's again the whole situation where you take the R vector prime squared, and that's just equal to the magnitude prime squared plus the magnitude times the phi prime all squared. And here's the orbital frequency. It looks like it's the first derivative, although I'm guessing it's really the second derivative because it wouldn't make any sense. Maybe. No, I have to double check whether it's the first derivative or the second derivative for the orbital frequency. But that is generally going to be good for orbits. Now let's look at the last topic that I was dealing with. It was kind of difficult, was these normal modes. So you got some oscillators here, coupled equations, and you're looking for the eigenvalues of W. So here's the determinant of k minus w squared m, which is how we find our w squareds. Sometimes you get the same frequency. That's just called a degenerate mode. Sometimes masses can move together without compressing the spring, and this is the zero mode. So let's take a look at something maybe like this. We have two springs, two masses, and the first potential, as you can see, is 1/2 k x1 squared. The second one has to do with both x1 and x2. You gotta subtract them and then square them. Now you can uncouple these by saying x1 equals the sigma 1 plus sigma 2, and x2 is sigma 1 minus sigma 2. And then, after you try to solve the equations of motion here, that will uncouple them. So that's one way to solve this. Here's another setup here. So we have two pendulums with a spring in between them. It's important, and we're setting an in phase, which is theta equals theta, out of phase, which is theta equals negative theta, and then here is the potential energy, 1/2 k I have a feeling this should be an L squared, but regardless, you're going to have theta 1 minus theta 2 squared, and because of this, when you replace this with, yeah, you get two different modes. So you can either do it in phase, and they become the same, and this equals 0, or you can do it out of phase, where you get 2 of the same angle here. Now sometimes we have to solve for x's and phis. So your equation might look like this. Just remember that the m vector goes with the or the M matrix goes with accelerations, and the K matrix goes with positions. And then you can solve kinetic energy. Here's another setup here. We have a spring, we have a mass, and we have a pendulum on that mass. So we have two positions, x1 and x2. We also have this little distance x here, which is, so x2 is going to be the sum of x1 plus x. And x is equal to L sine of theta. You can use a small angle approximations here. You can get y2 is going to be equal to this small piece, but with the small angle approximation, notice how we kind of have a squared, and the square of the small angle is 0. So yeah, the kinetic energy here is just going to be x squared plus y squared, and in this case, since y prime is 0, then we just focus on the x squared kinetic energy. Here's another setup. We have two pendulums, one sort of attached to the other. We always want to measure the angle from the vertical, not the horizontals. And because these are pointing down, we have to put a minus sign for the R, for the Y position. And just using angles, we have L sine of theta, L cosine theta. Do some small angle approximations here. Do the velocities, and again, small angle approximations there. Okay. Now, to solve these modes of oscillations, we have to also look for the eigenvectors, not just the eigenvalues. So after you solve the equation, the determinant here, this is like a characteristic equation, you also have to solve this equation for the eigenvectors. So this is relatively easy, but once you do that, you will find 2 or 3 or whatever different eigenvectors. One of them might be symmetric, 1, 1. One of them might be antisymmetric, -1. Here's the zero mode again. It should have been up here. But the zero mode is essentially as the limit of w goes to 0, our solution here is actually going to approach a plus ct. Just because if you plug a 0 in for the cosine, it goes away. And if you kind of plug a 0 in for here, it doesn't go to actually 0. It goes to t, or wt really. But anyway, so the zero mode is approaching a drift. That's exactly what this looks like, a little drift. Constant motion. Now, usually you'd have to sum up the different positions, so you could do it like this. Position 1, position 2 is equal to the amplitude 1, and I've just normalized it here. That's why I've got the square root of 2. But you don't need that. So now we have amplitude 1, and then you're going to multiply that by the first vector. Amplitude 2 multiplied by the second vector, and of course you have the appropriate frequency attached to that. Now it's important to notice how to interpret this, because if they're both positive here, then they're both moving in the same direction, yeah? But that means that if the amplitude is exactly the same, 1 and 1, that means that the coupling string between them isn't stretched. In order for that coupling string to be stretched, for them moving in the same direction, then they need to have different amplitudes. But since they have the same amplitude, moving in the same direction, the string in between is not stretched, in this case. Over here, we have the things moving in the opposite directions. One is positive, one is negative. And that means that the string between them is going to greatly stretch, even though they do have the same amplitude. So this is how you want to interpret these modes. Cool thing about the K matrix and the M matrix is that you can use the Hessian for the potential. It's kind of these partial derivatives here. And for the M matrix, you can basically just look at the coefficients of the kinetic energy. These ones remove the 1/2, these ones keep the 1/2. Alright, a couple little tricks here. Sometimes when you're solving for the frequencies, notice how you can square root both sides. Oh, no, sorry. This one here shows you the zero mode, because if you get a w squared and a w2 here, pull out the w2, and then that one equals 0, and then this also equals 0. So there's a zero mode right here. In this case, usually what happens is you get some simplification where you have to square root both sides. It just makes the math easier. But if you do that, you have to take both the plus and the minus, so you get two answers. And here's some ways to set up the eigenvectors. If you have v2 equals 2v1, then you plug it in like this, where 2v1 is equal to 1 over 2. And then over here, if you have 0, v1 equals 0, then v1 is clearly equal to anything. B v2 equals 0 means that v2 equals 0. And so you have this vector right here. That basically covers most of the stuff that we want to remember for mechanics. So, man, it's definitely very complicated, and there was a few things that I'm a little confused about, but hopefully this was somewhat helpful. Cool. Y'all have a great night. Thank you so much for watching.